Recording. Good morning, ladies. So today we'll start off by finishing the last part of this chapter, which is what's known as RC circuits. So we'll finish these RC circuits, and then we'll do a quick review of what to expect for tomorrow for the exam. And then after that, I have a couple of group assignments for you. So that gives us, I think, 7 total group assignments. I think that's correct. So unless I miscounted, which is always possible. So good. So let me share my screen, and let's talk about RC circuits. Somebody else is trying to come on. Okay. So RC circuits. So an RC circuit is basically just short for a resistor and capacitor circuit. So basically, all we're going to do is connect in series, at least for now, a resistor directly connected to a capacitor, and then we're going to look at 2 different scenarios. So the first scenario I'm going to look at is the charging case. So basically here I'm going to take a power supply, so my EMF, so this is the positive side and negative side, and we're going to connect that to the capacitor where initially there's going to be no charge. So basically, if you want to imagine, there's initially some switch here, and then we're closing this switch at time is equal to 0, so that there is 0 charge initially on this plate. Okay. So that's going to be the first scenario we're going to look at. And then after that, we're going to look at discharging, which is we're going to charge up our capacitor, take it out of this circuit, and put it into another circuit which only has a resistor and a capacitor. And we'll see what happens in that case. So let's talk about this. So here, so first off, let's kind of schematically talk about what's going to happen. So initially what's happening again is that when I have the battery, I'm going to close the switch. So initially there's no charge moving through the circuit. There's no current. There's no anything. And then I'm going to close this switch again at t is equal to 0. At that point, I'm going to now start having charge carriers. So this is going to be my little Q. It's going to start moving through my circuit. So it's going to create a current. So my current is then going to start moving through because of the resistor. We know the resistor is going to cause the current to move through, which means that I'm going to place 1 positive charge then onto this plate. So as time goes on, I have more and more charges which are now trying to be placed onto this plate. So now I have another charge that I'm going to put onto this plate. So as time goes on, what's going to happen then is what? More and more charges are going to be put onto this plate. So the plate is going to start reaching its maximum charge. And as that happens, it takes more and more work to actually put these charges on, which means it has to do more work to bring these charges on, which means the flow of charges is going to slow down, and it's going to get slower and slower and slower until this thing actually reaches maximum charge. Once this thing reaches maximum charge, there's going to be no more flow of currents, which means the current then is going to go to 0. So effectively what's happening is when I close this switch, the current is going to be running at its maximum. There's going to be 0 charge on the plate. And then as time runs on, so at, say, t goes to very large, what happens in this case then is that the charge will start approaching the maximum charge, and then the current is going to slow down to basically 0. Okay. So if I plotted these things, so for example, what will happen then is if I plotted the charge versus time, what will happen then is I start off at 0 charge, and then this thing is going to asymptote to the maximum amount of charge, where the maximum amount of charge is dictated by the fact that there's no current running through, so it acts as if the resistor doesn't exist. So it's then only going to be determined by Q maximum is equal to C times that of the battery. So this is going to asymptote to Q max, where Q max is going to act as if the resistor doesn't exist, and this thing only reaches the maximum charge, which is based on the capacitor and the battery. So it's going to be C times E. So again, what's happening is time is equal to 0. I have 0 charge. At some later times, a very large time, this is going to asymptote to the maximum amount of charge. If I plotted the current is basically going to do the opposite thing. So the current is going to start off at the maximum amount of current. So let me call that I max. And that's going to asymptote down to 0. So it's going to end up going to 0 somewhere down here. The maximum current, since this thing has no charge on it initially, the maximum current is going to go through as if the capacitor doesn't exist. So it's only going to be dictated by the resistor. which means the maximum current is going to be dictated by Ohm's law, which says that the maximum current is then simply going to be equal to the EMF divided by the resistance. So this is going to be our maximum current. Now, the way we would usually fundamentally have to do this would be to use Kirchhoff's loop rules. So let's apply Kirchhoff's loop rules to this, just so we can see what this thing looks like. Now here, there's only one loop, so we only have to go around the circuit once. So I'm going to start here at this corner, call that point A. Go around, so the first thing we're going to go across is the battery. I'm going from negative to positive, so that becomes a positive battery. We're going across the resistor in the same direction as the current, so that becomes a minus I times R. And then I'm going to go across the capacitor from the positive side to the negative side, so that becomes minus Q divided by C is then equal to 0. Now what we know is that current is equal to the change in charge divided by change in time, so I'm going to write that as actually a differential. So this thing actually becomes E minus R times the rate of charge divided by time, minus Q then divided by C is equal to 0. So Kirchhoff's loop rule says that if we want to know what this thing is actually doing, we would have to solve this expression. Now, fundamentally speaking, this is what's known as a first order differential equation, which is kind of beyond calculus. So we're actually not going to solve this. So I'll just tell you what the result is. So basically what would happen is, again, if I plot these things, what will happen is this thing starts off at 0. The charge is going to increase kind of rapidly initially, and then it's going to start to slow down because it becomes more difficult to put more and more charge on there because of the work. And this thing is going to asymptote eventually to get to that maximum charge. Here, the current starts up at maximum, but then it's going to decrease rather rapidly as the charge is increasing rather rapidly, and then it's going to slowly go to 0 as the charge is still slowly building up onto this. Okay. So this is what our two plots would look like. So again, here, close my switch at time is equal to 0, 0 charge, increases charge pretty rapidly, almost linearly initially, but then slows because the work becomes greater and greater and greater. So the rate at which I'm putting that charge on is going to get slower and slower and slower until eventually, very slowly asymptote to the maximum amount of charge. So what this says is that the charge on the plate as a function of time is equal to the maximum charge, which is C times E, times 1 minus E to the negative T divided by tau. There we go. Where tau is what's known as the time constant is equal to R times C. So this is what's called the time constant. For the current then running through the resistor as a function of time then is equal to the maximum, which is going to be E divided by R, times E to the minus T divided by tau, where tau is again that same time constant. This is the time constant. So this is what's happening in an RC circuit. So when we did the capacitor lab, you would actually have seen this if we did this in a regular semester. So we would actually have charged up the capacitor doing this. So what you would see is when you connect this originally to the battery, in this case, it would be a light bulb, which would act as the resistor, would shine bright initially, but then would get dimmer and dimmer and dimmer and dimmer as the current is getting slower and slower and slower until eventually this would have no brightness to it at all, at which point the capacitor would then be maximally charged. So when we are charging then the capacitor, again, what happens initially at time is equal to 0, we close the switch, we have 0 charge on the capacitor, so this is on the capacitor, and we have maximum charge running through the resistor. As time goes very large, technically infinity, here, maximum charge, or the charge will then approach the maximum charge, which is then simply equal to C times E, and then the currents will go to 0. So this is, again, across the capacitor, and this is across the resistor. So for charging, that means that what we care about is, this is the charge as a function of time, again, on the capacitor, and this is the currents running through the resistor as a function of time. Now, we can see that all of this is included inside of here because an exponential raised to the 0th power is 1. So at t is equal to 0, I have 1 minus e to the 0, which is 1. So I have 1 minus 1, which means we have 0 charge. As time becomes very large, i.e. time goes to infinity, I have e to the minus infinity, but e to the minus infinity is 0. So I have 1 minus 0, which is 1, times ce, which is the maximum amount of charge. Here, at time is equal to 0, I have e to the 0, which is 1. So I get simply E over R, which is maximum current. And then as time goes to infinity, again, I have E to the negative infinity, which is 0. So this thing goes to 0. So this matches exactly what these plots are telling me. Now, what happens if I discharge? So let's talk about discharging. So for discharging, what we're going to do is we're going to take that same capacitor out of that circuit so that it has some sort of initial charge. So let's say initially this is charged to Q0. And I'm going to attach that to simply a resistor. And then let currents run through the system. So here what will happen is initially this is going to be at positive Q0. This plate's going to be at negative Q0, but it doesn't want to stay charged as long as this thing is attached to the resistor. So what'll happen is that these positive charges here will start to flow in this direction, creating a current, until eventually what will happen is that there'll be no charge left on this capacitor and no charge left on this plate, so that eventually what'll happen is this will become neutral and this will also become neutral, at which point in time currents will cease to flow. So initially, when I hook this thing up, current is going to flow through the resistor. The charge will be at whatever the maximum amount of charge is. So this will correspond also to the maximum amount of current, which we're going to simply call I0. So that's going to be the initial amount of current. And then eventually this charge is going to dissipate. So all the positive charges will move to the negative plate. So this will become neutralized and this will also become neutralized. So here we have at t is equal to 0. We have Q is equal to whatever the initial charge is, and we have I is equal to the maximum amount of current, which we're going to call I0. Then as t goes to large, again, technically infinity, Q is going to go to 0, and I is also going to go to 0. So here, if I plot these two, so now if I plot Q versus time, initially this is going to start off at Q0. Again, it's going to asymptote to 0. So if I plot this, again, the charge is going to dissipate rather quickly and then start to slow down and then slowly asymptote to 0. If I plot then the current as a function of time, so this is I, this is T. So again, this is going to start off at some I0. Again, here, the current starts off maximally, but then is going to decrease rather rapidly. And then again, slow down as the charge is going to slowly move off the plates and then also asymptote to 0. So for discharging, the difference is now that the charge across the capacitor is now equal to whatever that initial charge is times e to the minus t divided by tau. And the current is going to be I is equal to whatever the maximum amount of charge is, e to the minus t divided by tau, where tau is exactly the same RC, which again is the time constant. So these are RC circuits. So we have the two different cases. So we have RC circuits when they are charging. Again, we start off with 0 charge, and then it asymptotes to the maximum amount of charge. Starts off with the maximum current, asymptotes to the 0 current. And then if I take it out and put it in a new circuit, I can then discharge it. So discharging, it starts off at maximum, asymptotes to the 0. For the currents, it also starts off at maximum and asymptotes to the 0. So RC circuits are actually used all the time in your daily lives. Pretty much anything that flashes or goes on a rhythmic type system is an RC circuit. So for example, your turn signal that people hypothetically use in Evansville, but nobody in Evansville actually likes using their turn signal, is an RC circuit, right? So when you turn it on, what actually happens is you're in this scenario, you're actually doing a charging capacitor. So what happens is you have the RC circuit inside of a gas. And what's happening is then you are charging up that gas by charging the capacitor, and then you're charging it, and then it flashes when basically you reach the breakdown potential of the gas. So when you reach that breakdown potential of the gas, that then discharges the capacitor, which basically causes it to flash, and then you charge the capacitor again. Windshield wipers are also RC circuits. So in that case, again, you're charging your RC circuits. When it charges maximally, it causes it to go up, discharges, comes back down, and then does it all over again. If any of you have a grandparent or parent or great-grandparents that has a pacemaker, pacemakers are also RC circuits. So you have an RC circuit, which again causes it to go up, increase, reaches maximum charge, causes it to discharge. When it discharges, it causes the heart to pump, for example. So RC circuits are basically used in anything that kind of flashes. So as long as you have something that flashes or goes off on a rhythmic type system, these are all controlled by some sort of RC circuit. So let's do a couple examples of this and see how this kind of works. So the first example, let's say take the capacitance in the RC circuits below to be 0.3 microfarads, the resistance as 20 kilo ohms, and the EMF as 12 volts. So here we're going to be charging our capacitor here. So first thing it wants to do is determine the time constant, and then the maximum charge the capacitor can have, and then the time it takes for the charge to reach 99% of this value, and then what is the maximum current. So these are all the things that I wanted. So let's do that one. So here we know the capacitor is equal to 0.3 microfarads. We know that the resistor is 20 kilo ohms. And we know that the change of potential, or the battery, in this case the EMF, is equal to 12 volts. Okay, so this is our EMF. Great. So first thing we want to know is, for part A, what's the time constant? So the time constant, we now know, is simply R times C. So it's just the resistor times the capacitor. So in this case, it's going to be 20 kilo ohms. So it's 20 times 10 to the minus 3 ohms, times then 0.3 times 10 to the minus 6. So it's going to be the same thing then as what? Kilo. That's a positive 3. Sorry about that. Not negative 3, positive 3. So it's the same thing as 6 times 10 to the minus 3, and it has units of seconds. So this is about 6 milliseconds. So this is our time constant. Part B, we want to know what is the maximum charge. Well, again, the maximum charge is simply equal to the capacitance times the EMF. So in this case, this is going to be the capacitance, which is 0.3 times 10 to the minus 6, times the EMF, which is 12. So it's going to be the same thing as what? 3.6 microcoulombs, right? So that's the maximum charge. Part C then wants to know, okay, the time it takes for this thing to reach 99% of its maximum charge. So for part C, we want to know that this thing reaches 99%. So this is going to be 0.99 times Q max is then equal to what? C times E times 1 minus E to the minus T divided by tau. So in this case, we want to know what is the time. Well, we know C times E is the same thing as Q max, so this is going to cancel with this. So we have 0.99 is then equal to 1 minus E to the negative T divided by tau. So I'm going to subtract this over here and add this over here. So I get an E to the minus T divided by tau is equal to 0.01. Now this is with a negative sign, so I'm going to actually multiply this over here. And then I'm going to divide this over here. So I'm going to get 100 is then equal to E to the T divided by tau. Is everyone okay with that? Because remember, an E to the negative is the same thing as 1 over E to the T divided by tau. So I'm just going to multiply this over here. And the 1 This is the same thing as 1 over 100. So I'm just inverting both sides. So, quick question. How do you get rid of an exponential? What is the inverse operation of an exponential?
Log.
Which one?
Natural logarithm.
There you go. That's right. So natural log. So we're going to take a natural log of both sides. So I get a natural log of 100 is then equal to the natural log of e to the t over tau. Mostly ask the difference because there's log base 10. There's also log base 2. There's log base whatever you want. So natural log is log base e. Good. So this cancels this guy. So it's going to be the same thing as t divided by tau. So finally solving for t. So t then is going to be tau times the natural log of 100. Good. Tau, we already know from here, that's 6 milliseconds times natural log of 100. So if I plug in my numbers, what I find is that works out to be 28 milliseconds. So it takes 28 milliseconds for this thing to reach 99% of its maximum charge. Finally, part D. So part D then wants to know, what is the maximum current? Well, again, we know the maximum current is as if the resist or the capacitor didn't exist. So the maximum current is just the EMF divided by the resistance. So it's going to be 12 divided by 20 times 10 to the third. So our maximum is then going to be about 600 microamps. 600 microamps. Okay, or that's 0.6 milliamps. If you want to do it that way too, 0.6 milliamps. Whichever one's your favorite, doesn't matter. They're the same thing. Good. Let's do one more. So the next one says we have a turn signal, which people in Evansville have no idea how to use. Flashes twice a second, so that the time constant is 0.5 seconds. So the RC circuit controlling this may have a capacitor of 1 microfarad. So we want to know simply what is the resistance of the resistor. Great. This one's nice and easy. So here we're told the time constant. So the time constant is 0.5 seconds. We know by definition that's equal to R times C. And here we know C is simply equal to 1 microfarad. So if we want to know the resistance, all we have to do is divide both sides by the capacitance. So it says the resistance then is going to be the time constant divided by the capacitance. That's going to be 0.5 seconds divided by 1 times 10 to the minus 6. So that's an equal to 500 kilo ohms. There we go. Which is the same thing as 0.6 mega ohms. Oh, sorry, 0.5 mega ohms. There we go. Mega ohms. Either one is fine. And that's about as much I'm going to talk about RC circuits. Right. So again, RC circuits, here it depends on what is happening. So if it's being charged, then you use these set of equations. So here, this is the charge on the capacitor as a function of time when it's being charged. This is the current through the resistor as a function of time while it is being charged. When it's being discharged, we now have these two equations, which now says that the charge on a capacitor now is equal to whatever the initial charge was, which could be the maximum charge or it could be something else. Doesn't have to be the maximum charge. This is just whatever the charge is at t is equal to 0. So this is just q equal to q0 at t is equal to 0, which again may or may not be maximum. And then the current is then equal to this guy, which again, this is the current at t is equal to 0. So again, may or may not be maximum. But again, time constant is exactly the same. So as far as the exam is concerned, RC circuits would only show up as a short answer quick calculation problem. Okay, so that's the only place that you're going to see that. Partially why I don't want to spend that much time on it, because they can get kind of confusing too. So for me, the fun thing about them is actually doing the math for it. But we don't do it in this class, so it's fine. Everyone okay? Like I said, RC circuits are mostly just there for, again, anything that does a rhythmic pattern. So turn signals. So again, if you're driving down the highway and you see flashing lights, and when you have construction zones, or if there's an accident, things like that, those are RC circuits. Windshield wipers, RC circuits. Pacemakers, RC circuits. So anything that does something on a rhythmic fashion, these are all RC circuits. Okay? They're controlled by RC circuits. So good. So that's it. We're done. We are now ready for tomorrow's exam. Nice. So let's do a quick review about all the equations and things that we need. So let's start off with chapter 18. So chapter 18, first thing we saw was current. We said the average current, or which we just called the current, was equal to the change in charge divided by the change in time. So again, all this fundamentally means is if I had a wire or some sort of resistor element, we would then cut out a cross-sectional area of it, of A, and we would count the number of charges which pass through this cross-sectional area. So this is our change in charge in a given amount of time, change in t. So this is what we call the current. What else? We also have Ohm's law. So Ohm's law says that the change of potential, or the potential applied across some sort of element, is then equal to the current times the resistance. So this just says that if I plotted the potential applied versus the current, this turns out to be a straight line, where the slope of the straight line is equal to the resistance. Resistance, simultaneously, is equal to the resistivity times the length divided by the cross-sectional area. So again, here's our wire or our element. So L, again, is simply equal to the length of this guy. A refers to that cross-sectional area here. And then, again, resistivity you can kind of think of as density. So again, resistivity is kind of equal to density. So similar to density. And again, this thing is material dependent. So different materials are going to have different resistivities. It's also temperature dependent. So we know that rho, as a function of temperature, is equal to whatever it is at the initial temperature times 1 plus alpha times T minus T0, where alpha here is also material dependent. So different materials will have different alpha values. Material dependent. What else we look at? So we also said that as electrons are trying to move through here, once I apply some sort of potential difference, and so if I apply a potential difference across here of delta V, what'll happen is then they're going to slow down, move at a constant velocity, and this thing is going to heat up, and this thing heats up and gives off energy due to thermal loss. So here we can then say that the power which is being lost, which is also equal to the power which is delivered, is then equal to either I times delta V, delta V squared divided by R, or I squared times R. Any one of these are the same, where these last two are specifically for what? Specifically for resistors. And this one is for any element, so anything. For a resistor, capacitor, battery itself, doesn't really matter. It's okay. Then we can define current density, J, which is equal to the current divided by the area. Now, if J is equal to a constant, in this case, we saw that the current then was equal to the charge of the charge carrier times the numbered density times the area times then what we call the drift velocity. So this is the assumption here, which means then that the current density J, write it as a vector, is equal to Q times N times dd, which is also written as a vector. Finally, we have the microscopic version of Ohm's law. So the microscopic version of Ohm's law says that the conductivity times the electric field is equal to the current density, where conductivity is equal to 1 over resistivity. So that's that kind. That was okay? Was it this chapter or the other chapter we did AC? I don't remember. Might have been this one. Well, we'll include it in this one, just for funsies. So let's talk about AC. So for AC here, we had a potential, which was equal to the peak potential times sine of 2 pi times the frequency times the time, which means that the current as a function of time is equal to the peak potential, or sorry, peak current, times sine of 2 pi times the frequency times the time, where the peak current is equal to the peak potential divided by the resistance. Here, the power, so the power loss, was then equal to the RMS value of the current times the RMS value of the potential, which was also equal to the RMS current squared times the resistance, which was also equal to the RMS value of the potential squared divided by the resistance. Where remember that RMS, so RMS current is equal to the peak current divided by the square root of 2, and the RMS potential is equal to the peak potential divided by the square root of 2. So that's these guys. I'll separate that. Good. So all that's AC. Now, again, we'll talk more about AC a little bit in the future, how we actually make AC and the usefulness of this. But again, the reason that we use it is because what? We can arbitrarily make the potential as great as possible, which means we can make the current as small as possible to have the minimum amount of energy lost as we transmit from one place to another place. So good. So that's all of chapter 18. So we'll come back to that. And next was chapter 19. So that's what we just finished. So chapter 19. So first off, we saw parallel and series. So let's do parallel here. Let's do series here. And then, oh, we'll do it that way? Yeah, we'll do it that way. That's fine. And then we'll do resistors and capacitors. Great. So resistors in parallel, we add them inversely. So we have 1 over Req is equal to the sum over 1 over the resistances. So we add them inversely. And in series, we simply add them together. So Req then is equal to the sum over I of Ri. For capacitors in parallel, it's just the opposite. So Ceq then is equal to the sum over all the capacitances. So we simply add them together. And in series, that's when we add them inversely. So 1 over Ceq then is equal to the sum of 1 over all the capacitances. Now remember, which is the other important part, is that in parallel, what's the same is the voltage. And in series, what is the same is the current slash charge. So currents for resistors and charge for capacitors. After this, we looked at Kirchhoff loop rules. So Kirchhoff's rules. So again, this is broken down into two rules. One is the junction rule, which simply says that at every junction, the sum of the currents going into the junction must be equal to the sum of the currents coming out of the junction. So again, this is just conservation of charge. The loop rule says that if I go around a closed loop, so if I have some sort of closed loop here, and I start off at, say, this corner here at point A, if I go around the loop, going from A back to A, the change of potential must be equal to 0. So if I start at A, go through my closed loop, come back to A, I have to have a change of potential equal to 0. So this is my loop rule. All of this is accompanied with some sign conventions. Let's talk about our sign conventions. So here, if I go across the battery in this direction, so if I go from A to B, my change in potential going from A to B is equal to simply positive of the battery. Negative otherwise. If I have my resistor, so here's my resistor. So in this case, it's going to say A, this is B, and let's say our current is going from A to B. So this is my current. In this case, then my change of potential going from A to B would be equal to negative I times R. So as long as I'm going in the same direction as the current, this is negative, positive otherwise. Capacitors, even though we have that rule, I'm not going to worry about it because that would only show up for an RC circuits, but we have other things to talk about for RC circuits. So I'm not going to worry about that sign convention. So the only two to worry about are just the battery and the RC, or sorry, the R. So good. So that's it for those. And then the last thing now are the RC circuits. So good. So for RC circuits, we have when they are charging. So for charging, we then have the charge across the capacitor as a function of time is equal to C times E times 1 minus E to the minus T divided by tau. And the current across the resistor as a function of time is equal to E divided by R times E to the minus T divided by tau. For discharging, we then have the charge across the capacitor is equal to whatever the initial charge is times E to the minus T divided by tau. And then we have the current across the resistor is equal to whatever the initial current is, E to the minus T divided by tau, where in both of these two cases, tau is equal to R times C. That's our time constant. So good. So first things first, let us talk about short answers. So as I already said, this is actually going to be a short answer question. So RC circuits will only show up in some sort of RC circuit. Okay. Other things that are guaranteed to be short ones are AC. This is also going to be a short answer. So that's the only place we're going to see that. What else? So let me diverge a little bit into long problems. So one of the two long problems is going to be Kirchhoff's loop rules. This will be one long problem. Let's call that long problem number 1. Which pretty much means that this other stuff here with parallel and series and all that good stuff, this will be short answer / extra credit. Okay. So going back, that means the other long problem is basically going to involve, I'm just going to circle everything here. Life will be great. Pretty much all this stuff. What is the chapter 18? It's all going to be a long problem. Okay. Good ones to look about this one are, things like I had the wire filaments that was running through, and then I asked you questions like, what was the electric field? What was the charge density? How much money did you have to pay? Things like that. There were a couple of them that had to do with charge densities and all that good stuff. And remember that charge density here, this is a constant, which depends again on the material. So this is material dependent.
If we're not solving for that, will that be given to us?
Yes.
Okay.
Yeah. So you'll have to know if it's, for example, a copper wire or gold wire or aluminum or, tungsten or whatever. So, yeah. So basically that'll be another constant that shows up on the front page. If you're not solving for it. But if you're solving for it, then you'll have to solve for it, obviously. Then you'll have to know everything else. So that brings us to then other things. So other short answer quick calculation stuff will also be just random things from inside of here. So things dealing with like Ohm's law, things dealing with resistivities and resistances, so things like that. So for example, this would also show up as a short answer. Trying to think what else is on a short answer here. Kind of Ohm's law and the definition of currents is also a short answer. I think what else is on here. So yeah, but those are the main kind of things. So yeah, so this is a short answer, short answer, short answer, and short answer. So that's at least 4. I can't remember what the last one. Oh yeah, this one. So that's all 5. Good. And then long problems, again, one of them will be a Kirchhoff's loop rule problem. And then the other one is, yeah, pretty much all of this stuff kind of mixed together. So again, examples for this one is look at some of the practice ones that involve anything using current densities and number densities and things like that. So those are kind of the examples. So other things to talk about, in case you do not have a TI 1 gazillion, which we found out yesterday that Callie does not. So Callie was now taught a new way of how to actually do that using the web. So a website known as Wolfram Alpha. So in case you don't have one of those 2i1 millions, you can use that. Callie knows how to do it now. So Callie has graciously said, if you want to know how to do that, she will teach you how to do that so she can get some more practice on how to do it as well. So if you don't have a TI 1 million, then just go ahead and contact Callie and she'll teach you how to do use the web to do it and do it that way. So
What was the name of the website?
it is Wolfram Alpha. So I'll bring it up for you. So it's Wolfram. So there it is. OLFRAM Alpha. Okay. So you'll just come on here, go ahead and click on this guy, and then basically you're just going to type something in here. And Callie said she'll show everybody how to do that. Whoever wants to do that, so go ahead and contact her. But basically what you'll do is you'll input some stuff here, and then just hit enter, and then basically it'll bring up the solution for you down in here. So
Is this acceptable to use on the exam?
yes.
Okay.
Yep. Yep. You have my blessing to use it. Right. You're now married to it. Life is great. Okay. So yeah. So even if you don't want to look up how to do it on your calculator, if you want to use this and go faster doing it that way, then yes, you can go ahead and do that instead. You have my permission.
I just shared my phone number on the chat.
Oh, okay. I was wondering what that was. Okay. So yes, so like I said, Callie knows how to do it. I showed her how to do that last night. So go ahead and contact her. Because again, she said she'd like some more practice on how to do it before the exam anyways. So yeah, go ahead and talk to her and she will show you how to do that. And then you can use this instead of your calculator. But yeah, either one is fine. Either one is fine. Yeah, so Tara, if you use that, don't feel like you're cheating. Everything's okay.
Okay, thanks.
You're welcome. All righty, so any questions on the exam? So typically this is an easier exam. So typically the average on this one is a little bit higher than the other ones, because again, this one is a lot more systematic. We're just kind of using definitions and more number crunching as opposed to seeing how all these things kind of mix together and all that kind of fun stuff. So not that anybody's doing bad in the class, but it's a good place to kind of make up some extra points. So yeah. So if there's no questions on that, so let's talk about our 2 group assignments then. So the first one is, we'll talk about this one. So when it's labeled Kirchhoff. So this one says that we have this circuit below. So here's our beautiful circuit. And then this says that the values of the resistors are, for R1, it's 1 ohm. For R2 down here, it's 10 ohms. R3 is 2 ohms, and then R4 is 5 ohms. And now we have 2 batteries. So we have EMF1, which is 12 volts, and EMF2, which is 5 volts. So what it wants us to do then is determine the currents. So it asks specifically for each resistor. Now, one thing I've seen in the past is whenever I ask a current through a resistor, students like to think that there has to be a different current through a resistor, just for fun. I don't know why. So, but here, as you notice that, again, everything here is connected in series, which means that the current running through resistor R1 and R2 are the same. So just because there's 2 different resistors doesn't mean they have to have 2 different currents. They will have 2 different potentials, but again, they're connected in series, so they'll have the same currents running through them. Then it goes on to say, is the battery EMF2 here being charged or not? Now, the way you determine if it's being charged or not is you look at the direction of the current. So if the current, for example, if we call this, I don't know, I2, if I2 is going away from the battery in this direction, that means it's being discharged. But if the current is going in the opposite direction, meaning the current is going into the battery in the wrong direction, that means it's being charged. Okay. So to determine if one of these 2 batteries is being charged or not, you just look at the direction of the current. So if both currents are going away from the batteries, that means they are being discharged. If the current is going into the battery, that means it's being charged. So that's like what happens when you take your cell phone, for example, and you connect it to the wall outlet. What it does is it actually runs the current into the battery, pushing it through in the wrong direction, which is actually what charges it. Okay? So if the current is going, again, if I call this I2 going in this direction, it would be charged. It'd be charged. Otherwise, if it's going in the opposite direction, it's being discharged. So in this case, you should find that the current actually is going this way, so it's not being charged. And then finally, it wants to know what's the potential difference between the 2 junctions. That's this junction here and this junction here. So if any of you have gone through any of the homework problems, you'll know that to find the potential difference from this point and this point, it doesn't matter how you do it. So for example, I could go through my circuit this way. So I could start at this junction, go around this direction. That would give me the potential difference, just whatever potentials across this line. Or I could start here and go this way and find whatever potentials across here. So that's also potential difference. That'll equal this potential difference. Or I can go simply across this resistor, and that's also the potential difference. Typically, the way I would do it is I would do the shortest, most direct way that has the least amount of stuff going on. So in this case, that would be this line going through here because this only has 1 resistor, so there's only one thing. So the potential difference in this case is just going to be this current times this resistance. So one other thing to point out about this problem is even though it looks a little weird, you can always redraw anything like this. So even though I have this guy's here kind of tilted away from here, I can easily redraw this circuit to make it look more familiar to you. And the way we can do that is we can kind of redraw the left-hand side. So again, let's put our resistor here. So this was what, R2. Here was our battery EMF1 connected to our resistor R1. And then down through here, I can simply move that and put this as R3. And then here's going to be R4 EMF2. Okay. So this schematic here is exactly the same as this guy. Let me move this kind of over here. These 2 things are equivalent. The only thing I did is I took this junction here and I slid it up to this point, and I took this junction and I kind of slid this whole thing down. but this circuit here is exactly the same as this circuit here. So the point is you can always redraw your circuits to make them look more like you're used to seeing instead of seeing this thing kind of off on the side. And the reason we can do that is because we always pretend that the wires here have zero resistance to them. We think of them as ideal wires, which means all the resistance in this section is simply that from the resistor itself. Okay? So that means if I shorten or if I lengthen a wire, it doesn't change anything because I don't have more power loss because there's no resistance in the wire anyways. So again, here all I'm doing is I'm taking this portion and sliding it down, and taking this portion and pulling it down and kind of straightening this wire. So this circuit here is exactly the same as this circuit. Okay. So that's group exercise number 1. Group exercise number 2 is basically similar. So this is now with 3 batteries. So this says we have R1, which is R1 here, 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 and here. All of those have 1 ohm worth of resistance. R2, which is this one in the center, now has 2 ohms interconnected to E1 is 2 volts, E2 is 4 volts, and E3 is also 4 volts. So this is 2, 4, and 4. And it wants to know what are the currents, both magnitude and direction. So here I didn't give you the directions, but at least I give you the magnitudes. So the direction just means is this one going in this direction, this one, and this one. So here notice that I can't have all the currents going directly out of the batteries. Because here if I had current running in this direction, running in this direction, and running in this direction, we don't abide by the junction rule because all the currents are going into junction A. I have nothing coming out, which basically means that one of these 3 batteries is being charged. Right? Because one of them is going to have current forced through in the opposite direction. So one of these guys is actually being charged. And then the last part is, what is the potential difference between A and B? Again, that potential difference I can either get by going this way, or this way. Either one is the same. And typically the way I would do it is I would go through whichever one is the least complicated, which in this case would be the center one, because now I only have 2 things. I have a potential increase from the battery, potential drop from the resistor. Here I have potential drop, increase, drop, drop, increase, and drop. So whichever one is the least complicated is usually the way I would go through it. So I would just go through here. Just like on this problem here, I would just go through here because now there's only 1 element, which is just a potential drop. That's basically it. So good. So those are the 2 group assignments. So again, both cases, you're just using Kirchhoff's loop rules. So you're setting those up, solving for the currents. Once you have those currents, then you can determine everything else from there. So.
I don't see the Kirchhoffs in the group assignments.
You didn't see them?
I'm not seeing it.
Did I not put them there? I could just be old and think I put them there and didn't put them there. So let's see. All right, so let's find out. Where are they? There they are. You are absolutely correct. Okay, let me put them there now.
Also, just like the little clarifying question,
Sure.
current into the battery is charged?
Current what?
Current into the battery would be charged?
Correct. So if the current is pushing into the positive side, then that would be charged. If it's moving away from the positive side, then that is being discharged. Okay. You guys are going to see all my hundreds of thousands of files. All right. There's the first one. Yeah, so if the current goes into the battery from the positive side, that means it's being charged, or just, yeah, charged. And if it's moving away from the positive terminal in the direction it should be going, then that is being discharged. Okay, so they should both be up there now. So just refresh your page and then you should find them. you find them this time, Callie? Yes, good. Okay. All right, so with our little bit of remaining time, so you got about 20 minutes to kind of start talking about these things. So I'll split you guys off into rooms. Hopefully nobody heard that. So that was my daughter screaming. She likes to scream. Okay. So anyways, here we go. Create our rooms. Okay. Hear them screaming. They're in breakout rooms now. So. I'm sorry. Everybody.
Be like independent or whatever. So the way he drew it like is so much easier.
Hello, everyone.
Hello.
Oh, I forgot to mention too, all of the folder for exam 3, all the submission files are all set up, so you can start putting up all the group assignments and extra credits and all that good stuff. So how are we doing so far?
I've got down the given information.
There we go.
I'm just a little worried because I don't think I would ever have been able to draw it like that myself.
Gotcha.
Like redraw it, which I know it's the same thing. It just like, I don't know. I guess I'm just saying if we have one of these, if you could just draw it the good normal way, that'd be great.
Well, I'll give you a hint. It'll look exactly like this one.
Like this one? And then can I hop on Zoom and you can help me?
That's fine. Yes. That's fine. I'll be around. Yep.
Okay, awesome.
Let me go check on the others.
Okay.
I'll be back. All right.
Okay.
So this side of the battery's positive.
Hello, ladies. How are we doing so far?
Just working on part A.
Okay.
Still.
I do have a question, actually. How did you redraw that picture again?
Oh, so basically, so let me share again. All right, so, and let me show you not in yellow. Yellow probably wasn't the greatest choice. So, let me do blue here. So again, so I had EMF here, and then I was connected to R1 here, connected to R2. And then basically the way that this was working is this came up to here. So this was then what, R4, EMF 2, and then this guy came here, right? And then this came down something like this, right? So this was then R3. Not the greatest picture, but basically something like that. So basically all I did then is I took this node and I pushed it up here, and I took this whole section and I pulled it down here. So I redrew this then as EMF 1, R1, R2, so none of that basically changed. And then I just took this portion and I pushed it down. So this now continues over here to R4. And then this was EMF 2. And then I kind of grabbed this portion and I kind of straightened it out. So now this came across through the center. So it looked like this. So this was the redrawn version.
So how did you know that R1 and R4 were in series?
Well, they're not. So here, because of this junction, they're not in series.
Okay.
That's right. And because of this junction down here, it's also not in series. So basically, what's true is that right, R1 and R2 are in series because these two are connected in the same line. But this is then in parallel with, so these two were in parallel with this guy and with this guy.
Okay.
That's right. So here, the easiest thing to do then would just be apply Kirchhoff's loop rules and not really think about, you know, what's in parallel and what's in series. That'll automatically be taken care of when you do Kirchhoff's loop rules. So
And you
here
just do that when you have the multiple batteries, right? That's when you don't have to.
Yeah, multiple
Okay.
batteries, you automatically do Kirchhoff's loop rules. That's right. Exactly. So here you might want to say, okay, I got current, I1 going this way, current I2 going this way, and then I3, say, going down through in this direction, right, to abide by the junction rule. So if I call that junction A, then you have what? I1 plus I2 is equal to I3. And then if I work with this loop, then I might go in this direction, so in the clockwise direction. If I work with this loop, I'll go in the opposite direction, so in the counterclockwise direction. So loop 1 then would be what? So if I start down here, so it'd be minus I1 R2 plus E1 minus I1 R1 minus I3 R3 equals 0. And then for loop 2, again, if I start in the same location, that would then be E2 minus I2 R4 minus I3 R3 is equal to 0. So these would then be my 3 rules that I would look at. Okay. Good. So basically now we have to solve these 3 simultaneously to then get the currents, I1, I2, and I3. And then once you have those, then you can answer all the other questions. Yeah. So the first part would be this. So this is what I would usually call the pre-solution. So basically working on all this stuff and then go through that way. Is that helpful?
Yes.
Good. Yeah. Just stop me if I talk too fast. And you're dressed very nicely today, Callie.
Oh, thanks. I went to it's like this women inspiring women breakfast. My mom woke me up and I got 10 minutes to get ready. So I just threw on earrings basically.
There you go. Very nice. And let me know when you're done copying Miranda, and I'll go so I can check on the other group. You're good?
I
Okay.
took a picture. You're good.
Okay. Good.
Oh shit, I should have done that. That's good.
All right. Let me go check on the other group. I'll be back.
Takes a while because they're all in different formats. So
All right. How are we doing here?
well, I,
Dealing with row
Oh, row reduced echelon form? Gotcha.
that thing.
Gotcha.
I didn't know how to pronounce it when I was in calculus, and I don't know how to pronounce it now.
Yeah, just call it RREF for short.
I think Jolie's the only one that has a calculator that will do that.
Oh, really?
I have it. I just haven't really figured it out yet.
Oh, okay. Like I have a scientific calculator, so I'm definitely going to be learning how to do it online.
There you go. Yeah, the best place to do it then is Wolfram Alpha. So yeah, it doesn't take very long to put it in either, so it's fine. It's fine.
Oh, that's good.
Yeah, I've never owned a graphing calculator in my life, so I can't.
I had one in high school,
Okay.
but between like high school and college, I lost it somewhere in the move. And I was like, I'm not spending $200 on a calculator that it doesn't say I require for this course.
Right. I don't know. I've never had a need for one,
Yeah.
especially with all the free stuff online, like Wolfram Alpha, or we have Mathematica site licenses and things like that. So there's no point. So it's fine. All right, it's me again. How we doing? Everybody okay?
Yeah, I'm honestly still just setting up my equations because I was just trying to do it myself. So
Always good practice. There's nothing wrong with that. Good.
yeah.
Now, Molly, you're a math major, right?
Yeah.
What kind of math are you thinking about doing? Are you going to go to grad school or just cut it short?
I'm actually pre-med.
Okay. So you're
Yeah.
pre-med with a math background, huh?
Yes.
I always thought you were biochem, Molly.
Mm-mm.
My bad. Aren't
I
you in
used-
biochem this fall?
No. I was in
Huh.
organic.
Maybe that's why I don't know. I know you from some class.
Yeah. I was actually biochem when I was freshman. I was coming in as a biochem, and then I decided I didn't want to do all those labs.
Gotcha. I don't think I've ever heard anybody do pre-med with a math background before. But
Yeah.
we've had a lot of people go through like biophysics,
Mhm.
physics background, but okay. I see you wearing scrubs a lot too. Are you at St. Vincent's or Deaconess or?
I'm actually working at an animal hospital.
Okay, veterinary hospital.
Yep.
I basically grew up at a veterinary hospital.
I used to want to be a vet, so
Okay.
Mm.
Gotcha. Yeah, my mom, trying to remember when, many years ago, she started working at one as a receptionist, and my brother and I worked there, and we used to volunteer there and do all kinds of stuff. So got to see some awesome things there.
yeah, it's fun.
Yeah. Very nice.
If that makes any sense.
Everybody still doing okay?
I think so. Jolie said that she didn't get the answers that you got, so we're going back over it. How did you write your junction rule?
Well, it depends. What direction did you say your currents were going? Which one are we looking at? First one, second one?
The first assignment.
Okay. So which way did you take your currents?
I defined both of the ones that are coming from a battery in the direction that the battery would be discharging.
Okay. Yeah, so this is the way I took it. So yeah, I got I1 going this way, I2 going this way, and then I3 going downward. So my junction rule then would be I1 plus I2 is equal to I3. And then for loop 1, so I'm looking at the left-hand side here, starting off down here. So I got minus I1 R2 plus E1 minus I1 R1 minus I3 R3 equals 0. And for this one, starting in the same place, I got plus E2 minus I2 R4 minus I3 R3. So those are my 3 equations.
Okay, so that sign should be different than I put.
Because going this way, you're always going in the same direction as the currents. So all of the i's would be negatives.
Okay. So I got myself turned around at the bottom where R2 is,
Okay,
and I gave it the wrong sign.
gotcha. Okay. Gotcha. And what were all the, okay, so you got, oh, might as well check all my numbers here. So let's see, R1 is what? Okay, so I'm gonna kind of multitask here. So 1, 10, 2, and 5. 1, 2, 2, and 5. R4 equals that. And the two batteries were what? 12 and 5.
12 and 5.
Okay. Well, I might as well show you how to use alpha then, since we're already here. So here, what you're going to do is type in solve with a capital S, square parenthesis, curly parenthesis, and then you're going to start inputting all of your equations. Now, the problem is that it doesn't understand I1, I2, and I3. So what you basically are going to have to do is use a different variable for each one of the currents. So I'm going to use I equal to I1, J equal to I2, and then K is equal to I3. So here you would do I plus J double equal sign to K, comma. That's your first equation. And then the second equation, well, let me move that down here. So I get a minus I times R2, where R2 was what, 10, right? Plus E2, which was 12. Or sorry, plus E1, minus then I1, which was I, times 1, because that's R1, minus I3, which is K, times R3, where R3 was what, 2? Equals 0.
Yep.
And then comma. Now we have the last equation. So my last equation then is going to be E2, which was 5, minus I2, which is J, times R4, which was... How much was R4 again?
5.
5, okay. Minus K times 2, because that's R3, is equal to 0. So once you input that, now you're going to put in another curly bracket to close. Oops. After that, do a comma, curly brackets, I, comma, J, comma, K. So that's saying what it is that you want to solve. So the way that you're reading this is it's saying solve these three equations. These are the three equations for these parameters, I, J, K. And then you just hit enter. That brings up the three equations and then tells you your answers here. So I1 should be 74 over 87. I2 should be 41 over 87, and then K should be 115 over 87.
Why the double equal sign on the first equation?
It's just the way Mathematica works. If you do a single equal sign in Mathematica, the way it then assigns that to a variable. So for example, if I wanted to say R1 is equal to 10, then I would just put R is equal to 10.
So could I just
single equal sign.
rewrite that equation equal to 0 then and not have to use the double equal sign?
Well, even then, so anytime you just use a single equal sign, it's assigning a value to that. It's not saying it's equal to it.
Okay, you've used the double equals all the way through. I got it.
That's right.
Okay.
Yeah, so if you don't use the double equal sign, it's trying to assign something to it, and it just confuses it. So, yeah.
Since these are like it's just a system of equations,
Mhm.
you also use like addition and substitution as well, right?
Oh yeah, of course. Yeah, yeah. You can do that. It's just going to take you 10 times longer, basically. So, but no, I mean, yes, automatically you can do that. That's right. So in this case, what you could do for this equation, you could solve for what I1 in terms of I3. solve this one I2 in terms of I3. So that way when you plug them in here, you get an I3 and an I3. So everything's equal to I3. And then you solve for I3. Once you have I3, you plug it back into this expression and this expression to get I1 and I2. So yeah. Any way you want to solve a systems of equation. The only thing me telling you how to do it this way or doing the row reduced echelon form is basically to try to save you that 20 minutes worth of algebra. Basically is about it. So.
Which on the test is valuable.
Yes. Yeah. But if you're, just doing your homework and you got all the time in the world, then yeah.
Oh, that's what happened to me on the last exam. I was like, I really wanted to do the extra credit, but I ran out of time.
It happens, unfortunately. But yeah.
That was me, except I really wanted to finish the second problem, but I just went out.
I know, and then my scanner was like, software needs to update, and I'm like, not now.
Yeah, it's always great when they decide to pick the worst time ever to do things like that. Yeah,
They always do. Like when you pull up, like they did it last night. I pulled up because I was like, okay, I really need to do this assignment, and I opened my computer and it was like, restart now because you need updates right now or next week. Like basically like next week is not going to work. And I was like,
right.
I'm sorry. Nope. Can't do that.
Yeah. And then of course it has to restart for an hour because it's updating things. So yeah.
Right.
Nice. There you go. All right, so it looks like we're officially out of time. So if you want, you guys can keep working. Looks like everybody else in the other room already left. They said, screw that. So, so it's fine. So yeah, if anybody has any more questions, I can answer those now. Otherwise, I'll see everybody tomorrow.
I have a question.
Sure.
How would you find the potential difference between the two junction points?
Okay, so here, so you see, again, the easiest way to do it would be across the center point. So the potential difference going from this point to this point would then just be equal to this current times that battery, or times that resistance.
Okay.
Oh, I stopped sharing my screen. Hang on.
Yeah, it's okay. I was following you.
Okay. But yeah, let me do that what we're actually looking at. So yeah, so the potential difference between this point and this point is either go this way, or go straight across through the middle.
Okay.
So again, the easiest is just go straight across through the middle. So
it would just be current times.
Yeah, so in this case, it would just be, so depending on which direction you're going, so if you want to just look at the magnitude of it, so the magnitude potential difference would just be whatever you get for current 3 times R3.
Okay.
That would be it, yeah.
Okay.
Or again, you can go this way, which would then be, what, E2 minus I2 times R4. Or if I go this way, it would be E1 minus I1 times R1 plus R2. So any of those would be fine.
Okay.
But as I usually, I always try to do the least amount of work, which in this case would just be I3 times R3.
Right. Okay. All right. Thank you.
You're welcome. Any other questions anybody has, or you doing okay? All right. Well, then I will see everyone tomorrow, at least during lab.